So we're very happy to welcome Antonina. She'll be giving a talk about learning from proofs.
Yeah, thank you so much, Susanna, and thank you so much for letting me come here. That's like really, really cool to be here and see all the great people in here that I didn't even know were here. So I still don't know what to talk about because I still don't quite know the expectations of the audience, because this originally was kind of a more general CS audience, general theory talk. If the audience wants a bit more newer and more detailed stuff, please speak up, because I'm pretty sure with the stuff that I have prepared right now, a lot of people that I see both here and on Zoom have seen it 10 years ago and probably going like, okay. So please speak up if I'm talking about things that you've seen before and you want me to do something more new and more substantial.
You're just raising the suspense, you know, this is unbearable. You have to talk, but I'm sure it's going to be exciting.
Yeah. Okay. So one of the interesting things that I've been kind of watching and trying to get on in the last few years was all the situation when people would take some known result, known proof, known something, and they would look at it from a completely different direction. And they would get some amazing stuff that probably when people, well, sometimes even people who originally did the proof said, oh, why didn't I think about it like in the 90s or 2000s? And part of it was this a big trend of taking something that was a proof, the proof of hardness, the proof of formal system, turning it upside down and getting great algorithms and getting very interesting results, proving new complexity stuff. Some of it that was fairly recent would probably be an example of it could be all the things with the range avoidance problem, which started as a very nice result in bounded arithmetic and was a very nice result in bounded arithmetic for like 15 plus years, and suddenly it became very big in complexity in general. And another one, the one that I seen kind of the makings of a little bit more, and the one that I could talk about, unless people tell me, oh no, I've heard it 10 years ago, go on to newer stuff, is when people take results in cryptography, turn proof of hardness on their head, and instead of proof of hardness, get learning algorithms, get interesting objects more in the AI realm than in theory realm. So in particular, so when you have proofs of stuff, if your proofs are constructive enough, and most of the times our proofs are constructive enough because that's kind of the way most of us think, then you get algorithms. If you get proofs of complexity statements, it's proofs about there is a circuit, or no, there is no circuit. For every circuit, you could find a mistake. You actually get learning just out of the definition, because if you get a way to construct a circuit out of whatever thing you are given, that's learning by my standards. So there've been a lot of different kinds of algorithms that you can get out of constructive proofs, but in particular, refuters and satisfiability and just ways to construct stuff. But probably one of the most kind of glaring example is really the learning algorithms. So mostly I'd be talking about learning circuits, formula, subclasses of circuits, but that's kind of the trend. Okay, so since this talk was intended for a general departmental audience, I apologize for introducing the non-uniform computation too. So what's non-uniform computation? For you need to solve a problem on inputs of different lengths. And in a Turing machine setting, you have one Turing machine that always works. In a non-uniform setting, you have a sequence of Boolean circuits. And I'm probably going to talk way more about the complexity of generating those circuits. But potentially, for every input length, you could have a completely different thing that does completely different stuff. And it's a very, very powerful model because if you put no restrictions whatsoever, it's very easy to solve undecidable problems with in the non-uniform setting. So yeah, you know this one. I want to solve the problem. I'm given a string of length n, and I want to know whether nth Turing machine holds en blanc. So what do we know about circuits? We know that nearly all Boolean functions require the circuits that are as big as they can possibly be. And this is the famous Shannon counting argument. You just say there are so many descriptions of circuits, there are so many functions, there are many functions that small descriptions of circuits. And also we know the almost matching upper bound that we need pretty much about that much size to write down many functions. And by the way, I'm sweeping a lot of stuff under the rug, but it doesn't matter that much. I'm thinking of circuits over and or not. You could throw in other stuff. Things change a little bit, constants change. You could talk about number of wires versus number of gates, but roughly it's the same. So here's another example of a fact about circuits. Parity cannot be computed by DNFs. And what I'm going to talk about is that there is a significant difference between the proof that nearly all Boolean functions are hard and the proof that parity cannot be computed by DNFs. And it's not just because we are talking about a single function, parity. It's actually not even the properties we need from parities are much more general. But the main difference is that the proof that parity cannot be computed by constant depth circuit is constructive. The proof that nearly all functions are hard is very much non-constructive. And whether it can be made constructive is a great question. So, oh yeah, and by the way, in case I don't know if there was anything newer since then, but the last circuit size lower bound for problem in NP is like n times 3 plus some number. And is it the latest, greatest number? Yeah. Okay, so let me just, with the danger of boring you, run through the proofs of Shannon's versus parity, because just to contrast them. So one is some Boolean function require exponential size circuits. Another one is some Boolean functions require exponential size DNF. Shannon's argument. There are 2 to the n Boolean functions on n variables. There are 2 to the 2s log s circuits with s gates. The rest is counting. Here is the proof for parity. Let's take a DNF with s terms. You look at the terms and 2 things happen. Either you find the term that doesn't mention the variable, and then you know for sure it doesn't compute parity because no matter how you set that variable, it will be, if the rest of the term evaluates to 1, the thing will be 1, so it's not parity. Or every term mentions every variable, but then there are way too few terms to cover all the possible assignments. And therefore, you need DNF with 2 to the n minus 1 terms to compute parity. just a running example. The first one is non-constructive, second one is pretty constructive. Questions, comments, more like yeah, go on, and all the stuff. Yeah. So some results that I talk about, and please tell me if you want to see more of something than other. A constructive proof of upper bound give you an algorithm to learn stuff, to compute circuits that, to figure out the circuits that approximate the function, for example. And there is both kind of a positive result that from natural proofs, you could get learning algorithms. It's an old result, but it's kind of probably the cleanest result of these connections. So you tell me whether you want me to go over it. And the second one is a little bit newer, which is if it happens to be that everything in polynomial time are computed by circuit of size n squared, it's not ruled out, we only have linear lower bound, then this has to be super non-uniform. And that extends for like NP and other classes. And the second one actually comes from bounded arithmetic. This was kind of interesting because started with bounded arithmetic and probability and realized that one of the things that bounded arithmetic gives us is something that's been known in the learning community since 1980s as Dana and Gluin's learning algorithm. Okay, so what about proofs of lower bound? And there is a ton of work by a lot of people in our community. I am only going to mention some of the things that I've been involved with. In particular, we just had a paper trying to figure out if there is a constructive proof of, well, Shannon, or more specifically, circuit size hierarchy. If you have circuits of size n to the a and a is greater than b, then you can compute more stuff than the circuits of size n to the b. And what we could show is if there is a constructive proof of that thing, and I'll define what kind of constructive in a moment, then you get circuit lower bounds, mild ones, but circuit lower bounds. So it's kind of this big interplay, proving hardness, you turn it upside down, give learning algorithm. You start with a proof, you go to an algorithm, you prove on possibility, you go back to proof, you get on probability, and yeah. Questions, comments, suggestions? And I will talk about bounded arithmetic, but please don't run away. I'll have 2 slides introduction to bounded arithmetic, which I hope is the gentlest one you'll ever see. Okay, just to say one reason why we really want constructive proofs of things like circuit size hierarchy and Shannon's. If only we could get our hands on hard function, it would make our algorithmic life a lot easier. If we could construct a hard function in linear exponential time, then randomness doesn't help with algorithm, and BPP collapses all the way to P. And a lot of things like polynomial identity testing, we suddenly can do deterministically, which means some people may want, some people might not. And the tool that we are going to be using, or not we are going to be using, but the standard tool for those kinds of hardness to randomness results is pseudorandom generators, where think about it as having an access to a function, which is a hard function. It's so hard you cannot tell it from random. So you might as well use it as a source of randomness. And then with a little bit of true randomness, you could get a much longer string than you seed, which still looks random. So yeah, this way you couldn't de-randomize. Questions, comments, speed up, slow down. Okay. So let me just very quickly talk about natural properties, just because this is one example of something that started as an impossibility result, talking about cryptography. You turn it on its head and you end up with a learning algorithm. Probably the cleaner, not very clean learning algorithm, but the cleaner framework in which you get it. So here is a very natural, in a direct sense, way of proving stuff. I want to prove lower bound for a class T of circuits or whatever I have. I know that nothing in this class has a certain property. For example, when we talked about DNF, one property of DNF is very high sensitivity. You flip one bit of DNF of a function, any bit, the value changes. So my special function, let's say parity tends to be special in a lot of cases, has this property. Parity has a super high sensitivity. Therefore, my special function is not in the class C, and I'm done proving a lower bound. What makes a proof natural is that oftentimes, whatever that special property, my function, makes my function hard, that the same special property that random function would have. Random functions have pretty high sensitivity, for example. What you do need here is that you need to be able to figure out whether a function has a property. If somebody gives you a truth table and says, yes, no, figure it out, you should have a deterministic algorithm to do it. But if you have it, great. So way back in 98, Rasborov and Rudich have shown as a way of a barrier that if you have a class where you believe you could do cryptography, as in have one-way functions or something like that, then you can really hope to have natural proof of lower bounds against this class. For example, the class of bounded depth threshold circuits, TC0, has candidate one-way functions. We cannot really hope to have a natural proof for it. But up until a little bit lower, by the time that they published that paper, there were all sorts of lower bounds. It just, they kind of got stuck. And so when they got stuck, the highest class for which natural proof was known and still known is bounded depth circuits with parity gates or with mod P gates for a prime P. As soon as you throw in mod M gates for an arbitrary number M or parity gates for two different primes, you end up with a class for which we don't know a natural proof, the class ACC. And for that, even though now we have lower bounds thanks to Ryan Williams, those lower bounds are not really natural. They're not built on the same template. Okay, so now in meta complexity, everybody talks about distinguishing chaos from order. Natural properties are an ultimate way to distinguish chaos from order. So just kind of semi-formal definition, you need three things for something to be a natural property. You have to be able to efficiently check if it's true, given a truth table. A random function should be likely to have it. And I mean, the last but not the least, you should be able to actually use it to prove a lower bound. Otherwise, why would you bother? The first one, the constructivity, had been the sticking point for a number of attempts to prove stuff. For example, an ultimate natural property could be minimum circuit size problem for whichever class you're dealing with. Except we know it's hard for DNFs and like bounded depth formulas, kind of, sort of. We really don't know and don't really believe, maybe, that we could check, given a truth table, if it has a circuit of certain size. If it did, great, so it would be natural property for this stuff. Okay, since I had no idea who's going to be in this talk, and I thought that maybe people coming from AI community, neural net community, I was going to give, so here's an example of a natural property from a neural networks realm. In our language, imagine you have one weighted arithmetic threshold gate. And if you only have one gate, the only thing you can compute are the linear separable sets. So you could only compute a function if you could kind of draw a line, a hyperplane with all the positive examples on one side and all the negative examples on the other side. Parity is very much not a linear separable function. But this is kind of an example of a property, a more general property. Now we're not just talking about parity. We say anything, if it's not linearly separable, perceptrons are not going to cut it. Questions, comments? Do you want me to say anything about this picture? Questions? Yeah, our knowledge stops at kind of at ACC or maybe even right before ACC. Natural knowledge stops right before ACC. We do know lower bounds. Okay. So so the result I wanted to mention as a clean example where you take a hardness proof, turn it upside down and get learning is rather than saying, oh, if we have cryptography, we cannot have a natural proof for the class. We say, well, the way the proof goes, the way the proof goes is like this. You start with a function, and if it's a hard function, you plug it into pseudorandom generator, out comes a pseudorandom string. So if you have a cryptography in the class, you could implement this kind of stuff. And reconstruction and the analysis, how you prove it, you say, oh, look, suppose somebody can break my generator. That means, well, you cannot break this, cannot break that. Oh, that means my function was not hard. Wait a moment, that means you can learn the function. Requires extra stuff, but that's the general idea. You take a hardness proof and turn it upside down. Rather than constructing a generator, thinking about constructing a generator and the output being hard, you think about the analysis of the hardness as being your algorithm. So proofs are useful, right? Maybe. So here's the whole outline of the proof. So suppose you want to learn a function. This function is easy, then it's in a class for which you have a natural property. It turns out that in order to implement Nissan-Wigderson generator, you really don't need much machinery. You need to be able to take parities and like in a bounded depth way. That's all. So if you take your function, you know it's easy, and kind of put a few extra things consistent of computed parity on top of it, you still get something fairly easy. At least if you are in a class of bounded absorptive disparity or above. And so now, though, you know that if you treated the output of this thing as a truth table, it would be a function which is easy because, well, the whole construction is in the class, say AC0 mod P. And so if you have a natural property, you have an algorithm that takes this truth table, looks at it and say, oh, that truth table looks completely random. Oh, wait, this came out of the random generator because the random generator was a small circuit function and it was a small circuit, therefore. So On the other hand, yeah, so you have a distinguisher which can always say, no, I don't have whatever my property is on output of the generator, treat it as truth tables, and says yes on half the functions, just by definition. And that's really all you need. I mean, okay, you also need to do some extra stuff. You need to amplify, you need to do predictor distinguisher, you need to do hybrid argument, but most of you probably have done it. It's an extra machinery that just part of the proof. You take the proof and you implement it, and then you get to learn an algorithm. And when we were working at it at Simons, we were thinking, oh, yes, that's great. And Markov really likes that idea, but what can we do with it? Well, you know, we need to be in at least AC0P. That's kind of limiting. Are we getting like if pigs can fly, then horses can whistle? And then at some point we go like, well, the only thing we could do is a learning algorithm for AC0 parity. Surely there is one around. And apparently there weren't. I think even now the only algorithm we know how to learn bounded depth circuit with parity is that weird implementing a proof of hardness thing. It's not quite as nice in some respects as.
Can you repeat what you just said? I kind of. So we have no what.
I mean, please correct if I'm wrong, but I don't think that there are more, I don't know, natural is an overused word, but a different kind of algorithms to learn circuits in AC0P.
I see.
Do you know of anybody? Yeah, because it's really like implementing hybrid argument is not the way you usually design algorithms. But that's an algorithm. And there are some caveats. So
Yeah. So you're going to mention probably the caveats. I wanted to ask you.
yeah, the caveats are, wait, did I? Yeah, fine print. We only can do it over uniform distributions. It's the way it is now, it's quasi-polynomial time, but that's because that Rasborough-Smolensky distinguisher is not strong enough to give us, if somebody can improve this, we automatically get improved running time of the algorithm. And one of the big problem is that we need membership queries. We actually need to look up specific places in the function, the ones that the generator wants to see. This is in contrast to the learning algorithm for AC0 by Lineal, Mansour, and Nissan, where they just take random examples and they learn Fourier coefficients and they add them. By the way, none of them is proper. Ours is not too proper either. But there can work with random examples. We could, we tried really hard to get away from membership queries. We don't see how to do it. That's kind of a big question.
And is this proof technique such that it cannot give proper learning, or is it more about getting?
I think there may be hardness of proper learning.
I guess it depends on whether the Rasborough-Smolensky generator can be implemented in AC0 one. We don't know that.
There is a ton of stuff actually that comes on top of it. It's not just NW generator. You need like to implement amplification. You need to implement distinguisher versus predictor stuff, hybrid argument.
But that's all constant there? I don't know.
I think at some point we thought that it was in situ, and then we decided it's not even in situ because of like it's all the standards of the randomness machinery just like piled up on top of each other. And yeah,
And for DNF, do we know proper learning?
isn't it hard? NP hard for DNF?
Oh.
Yeah, something like that. Yeah, I think like 3-term DNF is already hard or something. Proper learning. Okay, I know it goes on record, so disclaimer. I'm not quite sure, but I think for proper learning DNS, we do have part. And please correct me if I'm wrong. I'll look it up later, and if it's wrong, I'll ask you to edit it out. Yeah. I mean, we could approximate things with greedy set cover, but we can't really proper learn stuff. Okay, any questions or comments? So this was one example of taking something that was a proof of hardness, flipping it around, getting a learning algorithm. And if you've been to any talks by Russell and Pagliazzi in particular, he's been working on it since then, and he has generative adversarial networks, he has some kind of dense model theory, consequences. He gets a lot of stuff, and I don't even know the latest state of it, out of just taking a hardness proof and turning it around. So apparently, for example, the proof of a hill, if you turn it upside down, becomes other boost. So the proof of there exists a hardcore set, and they're the same thing as the boosting algorithm. Okay. So so far I was just talking about natural proofs, which are, well, kind of natural, but not too formal. Another question is, what really constitutes constructive, and how do you measure degree of constructiveness? And one way of doing it is to say, if you can formalize it in the theory of reasoning of certain complexity, then because proofs in those systems very, very constructive come with algorithms, then you do get constructive proofs, and moreover, you know exactly the level of constructiveness. So in the last few years, there's been quite a revival of bounded arithmetic. So a number of people have proved very cool stuff. I guess I will be mentioning it later, but Igor Oliveira has a whole program of proving stuff. Albert Tatseri has proved really interesting things. And Jan Pich had been on a program of getting things done. Moritz, and like, I'm not mentioning a lot of people, but a lot of very good people are now actually looking at bounded arithmetic and proving stuff.
You're saying in a formal sense, a very non-constructive, or like Shannon's counting argument is somehow also mathematically deep in the sense that you need high-powered machinery to formalize it.
Yeah. Yeah. And one of the results that I want to talk about is actually that if you can formalize it, you get lower bounds.
Mm-hmm.
Okay. So now the slide you were all reading, introduction to bounded arithmetic. Hopefully the most gentle one is. So what's bounded arithmetic? What's arithmetic? You have numbers, variables, plus and times. And you know basic things about them, like x times y plus 1 is equal to x times y plus y. They're just the same axioms as in piano arithmetic minus induction. The way I like to talk about arithmetic from more computer science perspective, we also have strings, because most of the things that we talk about are strings. So let's throw in strings, finite length strings, and we'll only have two things, two operators with strings. One of them is look up an index, 0, 1, and another one is to check its length. And let's say for convention that we put 1 at the end of every string just because.
Did you say anything about, are we assuming anything about the alphabet here? Like we have an infinite number of symbols, or in a binary alphabet, or just a fixed sigma? Or
you could have just a 0 and successor. You could have a 0 and plus and times. So, sorry, 0 ones plus and times. That should do it. Yeah. Or you could throw in all the integers. Generally, I guess when people talk about those things, they assume natural numbers. But I think you could just define them starting from 0 and 1. But yeah, let's say all the natural numbers are there to make our life easier. Actually, yeah, natural numbers are good because we want to be talking about whether things are true or not over natural numbers. So yeah, is that what you meant?
Maybe.
I'm not
Let's
going to do
continue.
anything non-standard. So yeah, natural numbers. I mean, you could talk about rational numbers as fractions. We're not going to talk about reals. I'm not going to talk about anything else. So let's say we have natural numbers.
Are we talking about like two different kinds of things? You say numbers and strings. They're
Yeah,
different.
numbers and strings.
They're two different objects.
So they're two different objects. And in those kinds of theories, which make my life, the connection between them is if you have a number and you treat it as an index, you could look it up, the corresponding bit in a string. And if you have a string and you take its length, you get a number. That's the connection between the two. And actually, the length operator happens to be much more powerful than it sounds from the way it's defined, because it gives you bounded minimization, maximization, turnaround minimization, and therefore it gives you induction for free. So all of those theories, just because they have length operator, have induction of the form if something is true at 0 and true at y implies true at y plus 1, then it's true at n. Oh yeah, by the way, and one important thing here is that we don't want things to get out of hand, so everything is bounded by terms in the theory. So if you have plus and times, you can't really build exponential things because we won't be able to. If it's a string, we want its length to be a polynomial and stuff. So is that okay?
I think my understanding is that we're in a world where like integers that exists, they are integers.
Yeah.
And then there are strings, and those I can think of as being over some fixed alphabet.
Yeah, you could think about them over 0, 1. That's what we tend to think about them. Sometimes people think about them as sets, and you check whether an index is in a set. So strings tend to be more characteristic strings than anything.
So in particular, for example, the last line, I'm trying to read it. Capital number means string. Capital variable.
Capital means string. Lowercase means number.
Which I can interpret as, for example, positions in the string.
Yeah. Okay. And the notation here is a little bit like this notation. It would just mean the length of x is at most n. It doesn't mean value of x as interpreted as number. We generally don't really interpret strings as numbers. So, for example, multiplying strings is not really there unless you go higher up. So, okay, this is a general framework. And now how do we get the zoo? We can get a big zoo of theory by a single axiom, additional axiom, where you start with a formula or a class of formula or schema, and you just say there is a characteristic string for this formula. So you could think about it as, for example, I want all formulas. Okay. If you go back to logic as in model theory or relational structures, you could think about a formula which takes some relational variables as its parameters. It could also quantify over them, but that gives you much more powerful theory. Theory logic. So second order existential logic by Fagan's theorem precisely captures NP, for example. Everything you can express in existential second order logic is NP predicates. This is one way of thinking about what those formulas are. I can throw in all the AC0 definable things, or all the NP definable things, or all the polytime definable things. And I could throw in the function symbols for them just because I can, without any change in power. Or you could think about it as throwing in just one complete problem. For example, I could say, by the way, I could always find a satisfying assignment to a Hort formula. They're pretty much equivalent. There are many ways of doing it, but this is kind of the same. It's a polytime reasoning if you've thrown in ability to say there exists a characteristic string for polynomial time definable stuff. Or there exists a characteristic there exists a string encoding the computation of a circuit evaluation is P-complete. And this is how I like to get a function for polynomial time. Not talking about Koba maximum, I'm not talking about Smash, we don't have anything like that. It's this framework. It's equivalent to the stuff that's been defined in other framework, but I just find it much easier to think about numbers and strings. Okay, so what do we have in those theories? We have VPV, and the V in front sort of indicates that it's a two-sorted theory for historical reasons. The way we talk about the power of those things is witnessing theorem. For example, Sam Bass proved, and actually he proved much more interesting theorem, but in particular, if you have a theory for polynomial time reasoning, that means that if it proves a formula of the form for every string that there exists string y phi of xy, it comes with a polynomial time algorithm, or more general term in your theory to compute the y. And moreover, the theory proves that it actually computes it correctly. We are going to need another witnessing theorem, slightly less known, and this one will, oh, wait. I'm really running out of time. This one will correspond to another learning algorithm. So what if you have not for all exists formula, but for all exists for all? Then rather than saying there is something to compute that exists because there are a bunch of for alls underneath, the only thing you could say, there exist constantly many terms such that one of them computes it, and if the first term did not compute it, it gave a counterexample that the second term can use. So what can it do? A ton of stuff. It can prove parity lower bounds. Thanks to NP, it can even prove a PCP theorem, which is a pretty substantial piece of math to prove, but it can. And if you want to see more, Maurice Miller and Jan Peek have the survey from 5 years ago where they talk about what can be proved. What it cannot prove, suppose I have a statement, such and such algorithm, primality testing algorithm is correct. What it will be? The algorithm outputs 1 if and only when there exists a divisor for the n. If I can prove it in PV, I have an algorithm to compute there exists a divisor. So if you can formalize correctness of polytime primality test, you actually can find can factor. So I don't.
So this is a conditional result though. That we have like unconditional results.
For
something interesting that's true, but you don't know how to prove it.
Well, we know unconditionally that if the world is so strange that all polynomial time can be done in size and squared, this cannot be proved in PV. And this is the same thing holds for any key. So in contrast, Cannon theorem gives us a language in sigma 2. For any case, there is a language in sigma 2 that's not in M to the K. I just learned recently that Albert's student, Carlos Cantera, I think, had a master's thesis formalizing Cannon theorem in the theory corresponding to polynomial hierarchy. I don't know if that can be done lower, but at least in theory corresponding to polytime hierarchy. But we are talking about much lower. We are talking about just polynomial time. Okay, so what do we get for the circuit size hierarchy? If we could prove circuit size hierarchy without talking about exponentially many things, or if we could prove it using polynomial time reasoning, then we get superlinear lower bound for polynomial time. Okay, just superlinear, but we don't know superlinear. So we just say that there is an epsilon such that there is a language in P which requires n to the 1 plus epsilon. And I think that's also unconditional. So there is other stuff that people have proved. For example, Marco Karmazin and Stefan Grosser have shown that if you could prove that palindromes are not solvable by non-deterministic Turing machines in time big O of n to 1 plus epsilon, and we know that it cannot be in big O of, I think, n squared, then you actually get NP is not in size n to the k for every k. Okay. Any questions, comments? Oh yeah, by the way, surprisingly, formula size hierarchy can be done in PV for specifically by building a refuter for parity and showing that you can do it with formula and squared, but you cannot do it with formula of size below n to the 3/2, and the proof comes from Subatovskaya shrinkage. Okay, so let me. So if you have for all exists, that kind of makes sense what kind of algorithm you get. You have for all exists, you get an algorithm to compute whatever's under your exist. What kind of algorithm can we possibly get from for all exists for all? Because there is an extra for all quantifier sitting inside, and what do we do with it? It was very surprising for us to find that what falls out of this is a very natural class of algorithms, of learning algorithms that had been studied way back in the 80s by Dana and Gloom. So the way she called that was learning with equivalence queries. And what this witnessing theorem, which technically only applies to universal functions, but you could do stuff to make our theory, it's a universal series, you could do stuff to make our series universal. KPT theorem tells you that there are only constantly many steps of interaction, constantly many equivalence queries. Every time so the student, say if you do it in PV, it would be polynomial times student, says, oh yeah, I think this circuit computes my function. Is it? And the teacher either says, yes, good job, or says, well, no, and here is where it goes wrong. So student takes this example and tries again. KPT witnessing theorem says that if you could prove it in the theory, this will terminate after constantly many steps. We don't know which constant, but it's a constant. So we showed a bunch of things along the lines of if polynomial time is in size n to the k for some fixed k, then still may be possible that there are circuits, but you cannot learn them even with this very powerful student-teacher algorithm. The teacher here is super powerful, can do anything. And that's unconditional. And the proof is by extending Santanam and Williams, who showed that you cannot have polynomial time algorithm generating it. So apparently you cannot even have the student-teacher interaction. And why we came up with student-teacher interaction? Because that's what KPT witnessing does. Okay. So for circuit size hierarchy, it's a little tricky because now we have 4 quantifiers. For every n, there exists a big circuit, such that for every small circuit, there exists a string, there exists an input. KPT doesn't go that far, but you could prove a similar theorem that generalize it and gives you similar stuff, except you have like an oracle in the or the central quantifier in the terms. And yeah, this is the result that I mentioned. If you could prove polynomial size hierarchy with this kind of reasoning, then there is a language in polynomial time which is not in size n to the 1 plus epsilon for some epsilon. Any questions? Any comments? So, what would it take to prove the circuit size hierarchy? And surprisingly, there is a system that Emilia Rabbit defined back in 2004 or something, that can formalize a ton of stuff. In particular, it can formalize a proof of circuit size hierarchy. So, what is the system? We know and love pigeonhole principle. Big pigeonhole principle is when you have way more pigeons than holes. Dual weak pigeonhole principle is when you have way more holes than pigeons, and you're asking to find an empty hole. So, for example, there are n pigeons and 2n holes, or even n squared holes. Find me a hole that doesn't have a pigeon. And it's very easy to find such a hole with a randomized algorithm. You pick a random hole. The vast majority of them are going to be empty. So this is one result that wasn't bounded arithmetic. It was great. You could do probabilistic reasoning and a whole bunch of stuff. Formalized hardness versus randomness. Lots of cool things. And then in recent years, Oliver Horton came about and said, hey, this is a very useful problem. I can do all sorts of cool things with it. And recently they used it for new lower bounds, and range avoidance is all the rage. But it's really just came out of dual weak pigeonhole principle. So what can this theory APC1 do? And by the way, I'm putting V in front because I'm doing strings and numbers. Original theory was just numbers, but there is a very clean equivalence between the two. And this is a zoo for people who care about the things like. This theory is just polynomial time reasoning plus you have a dual weak pigeonhole principle, which gives you a way to find an empty hole. That's all. For every polynomial time function, you could apply dual weak pigeonhole. So it can show existence of hard function. It could prove the circuit size hierarchy. And although it's not super powerful, because at the off chance that SAT is in size poly, it doesn't prove it. So in a way, those consistency things, they say it's much more likely that, say, P is not in n to the k, size n to the k for every k. Because if it really is the case, it will be super hard to prove. So interesting things out of that is also that it is possible that there are P is not equal NP, but NP is in size P poly. But you cannot prove it with polytime reasoning. Okay. And I'm running out of time, and probably you've seen this stuff before. At this point, the question is, what about proving independence? I would love to prove independence of bounded arithmetic. I don't have anything yet. Maybe you could. The only thing I know about independence is that if P is independent, if P versus P is independent of essentially Peano arithmetic, then for all practical purposes, P is equal to NP, because that means that finding an error is like finding the next error would take such a long time, you cannot even talk about it in Peano arithmetic. Okay. So open problems, of which there are many, some of them more general than others, but I think I was going to just mention the most general ones. For the natural proof one, we would love to both apply this idea to get more algorithm and to get rid of those membership queries somehow. Can we just learn from random examples? Or can we get rid of the uniform distribution assumption? We could go up to product distribution, but that's not saying much. There is a program, I think Igor Oliveira is publishing a lot of cool stuff there, and other people. What is exactly reasoning power needed for the statements? And Igor have shown equivalences that like proving this bound is equivalent to some axiom that defines a theorem. And we'd love to show that some things are just independent unconditionally from systems of arithmetic, but we don't really have it. I mean, you cannot prove totality of exponential function. Well, yeah, because exponential, but that's about it. And of course, we'd love to get explicit hard functions. Okay, I'm just 1 minute over time, so thank you so much. Questions, comments, solutions, pointers to important results that should be on the next iteration of this talk.
There was a comment in the chat saying that it should be noted that that theory, whatever theory that is not verifiable. Is it clear what this is a comment for? Just for the last few minutes, that theory is not verifiable.
This was just in reference to the independence result from piano arithmetic, that you have added all of these true sentences, but in the theory, and now you can never tell whether a true sentence is really true. So even if I give you a proof, you cannot check that the proof is correct. So it's a bit of a strange theory. That's what I meant.
Yeah, that's a bit, that's a bit of a strange theory because it's piano arithmetic with all the true pi1 statements thrown in. And then they make a disclaimer that, well, we don't have any techniques that would differentiate between the two. So it's kind of morally the same. But yeah, you're right now. It's not verifiable. Yeah. Thank you.
So regarding the question of regarding the study, the question that's adding which principle can prove which result. It seems to me like you're trying to build a web of reductions of principles. And actually, your question is, this reminds me of what TF&P is doing.
Maybe you should repeat the question also.
Yeah, so I'll try to repeat it. So proving equivalent, like bounded reverse mathematics, proving that certain result is necessary and sufficient for a theory. You said it's like a web of reductions.
Yes, like adding what principle can I prove this result?
Adding what principle can I prove this result? So I guess, okay, to be honest, it's better to defer to Igor because he proved a bunch of stuff and sometimes he proved equivalences, but I cannot think of a specific one on the top of my head that I would be sure I won't be messing up. But he has this program of bounded reverse mathematics of actually pinpointing exactly that proving such and such lower bound is equivalent to dual with pigeonhole. So, for example, existence of hard function is equivalent to dual with pigeonhole. That was already in, I think that was already in the Mills thesis. I'm not sure though if it answers your questions.
I'm happy with that.
Okay. Yeah, that would be a question to Igor, but I don't see him in the list of people. Okay, more questions, comments, suggestions. Oh, thank you so much. Thank you.